Aló.
Vea, posso começar.
Vea.
Bom dia, good morning, everyone. Welcome to the fourth winter school of the Valongo Observatory of the Federal University of Rio de Janeiro. So I just wanted to, this is going to be a brief welcome, and it's going to be mainly to give you a few announcements, introduce you to a few people very briefly before I leave you with Manuela. So first, I just wanted to let you know, so this is the fourth winter school. The first winter school was in 13, sorry. So 2013, then we had 2015, 2017, this is the fourth one. And we are actually repeating the venue. The last edition was in here also in the Planetario, and since it worked so well, I mean, some of you were here, it actually worked so well. The Planetario team was so welcoming and so helpful that we were like, okay, we're not leaving this place. So we're very happy to be able to organize the winter school here again. So first, thank you very much to the team of the Planetario, the director of astronomy, Sherman, who will speak briefly in a moment. But aside from that, I just wanted to let you know most of you are from Valongo, but some of you are not. So just wanted to let you know a little bit about the graduate program in Valongo. It started in 2003 with a master's degree, and we're nearly achieving the first decade with the PhD. So this is actually very exciting. We've had how many PhDs up to now? What's the number? 16. So 16 PhD students have finished in the first almost 10 years. I think it's 9 years this year. So that's actually very inspiring. And uh, we have we're actually coming to a moment that it's actually been quite difficult. Education, science, research is uh, uh, last times, but especially now, there are a lot of cuts that we're suffering. So I think it's very good to take advantage of this kind of local event, which they're actually hard to organize. They will be even harder to organize in the upcoming future. So this is just a call to take advantage of these local events, take advantage of the presence of people who would normally not be close to your institution. So to the students, to the participants in general, just really try to make an effort to connect with the people that are here from outside of the state or from outside of the country. So, so it's we need to help each other as scientists, and this is the way to do it. Just really work on that networking. So this is I I hope you will take advantage of that opportunity. So I wanted to also introduce you to briefly to the local organizing committee and also a few members of the science organizing committee. So I will ask you to please, can the log and soccer people stand up? There are many. So it's not half of the room, but it's a fair amount. So we have I will not actually introduce them all, but you saw them. So if you have any question, ask any of these people. We're here to help and to really try to make this experience the best that it can be. There are a few events that we've organized on purpose for you to maximize what you get out of this of the school. First, there's the opportunity. Those of you presenting a poster, some of you actually brought your poster. I didn't actually check, so I don't know how many posters are up there. But the idea is that you bring your work and you discuss your work during coffee breaks. So put up your poster if you haven't. If you didn't bring a poster, make sure that you talk to people that have a poster or talk about your work. It's always good to have an elevator version of your research. That means that you can explain your research in under 2 minutes or something like that, depending on how many. 1 minute. So really exercise this. So you're in a somewhat protected environment to do this. So train it here. You can start your stuff afterwards when you go to other places too. There's going to be, as you know, the people who said that they were going to bring a poster, an opportunity to present it orally. So we call this the flash talks. So you have one slide, and just very quickly in 1 minute, 2 minutes, you will say what you're actually presenting here. This will actually happen today and tomorrow between the two speakers of the afternoon. So just before the coffee break, precisely so that you have the coffee break to talk about it. So I I I, I hope everybody who brought a poster will actually take advantage of this. Do not be afraid. We're not here to make you feel uncomfortable. On the contrary, it's really to get to know a little bit more about your science. So all of you who have that, have your flash talk ready, send it to either obws at astro.ufrj.br, which is the winter school email. Or should I?
That's me. Sorry.
Okay. So send your flash talk, send it as a PDF. You can either send it to Marco, so that's grossi, arroba, Luan, which is Elgezi, I think, Elgezi, or OVWS. So please send your PDF so that we know who is going to present today or tomorrow. We're going to distribute it depending on how many actually of you send it. Aside from that, there's also we have organized also speakers with sorry launch with the speakers. So if you haven't already, you can actually sign up to have lunch with one of the speakers, or maybe all the speakers will go together. That kind of depends on how things are organized. But this will happen every day. So take advantage and tour around each of the speakers. It doesn't matter if you don't work. I mean, if you work on galaxies, but you are interested in learning more about the Milky Way, about stellar populations in the Milky Way, or about protoplanetary disks. Doesn't matter. But it's always good to actually talk to other people who have another trajectory, another life experience with astronomy. So take advantage of that and have lunch with all the speakers. I highly recommend that. So aside from that, we're actually trying to make a slightly, as much as possible, eco-friendly, environmentally friendly school. So they're very small things, but they're small efforts. First, I think they're made with scrap paper. Yeah. Okay. The cadernos, so the booklets, are they made with scrap paper? Yes or no? Yes. Okay. So Denise's is not, but most of your booklets, it might be confusing. They have one side that is printed, but it's a way of just using the scrap paper that we had lying around Valongo. So we had a student, Aline, who was sort of leading that effort with other students. There's also to drink water. Do not despair. There are cups, but they're just paper cups. So Thiago right now is taking out a paper cup, and you can use it again. But it's a little bit of water each time, but you can just stay there and talk to the people who are drinking water. So that's what. And another thing is, if you got the last email and you read it all the way to the end, we asked if you could bring your own mug. I have a mug for me, for Thiago, for one of the speakers too. So bringing your own glass. I actually did a lot.
Thanks, Karen. Hi, good morning, everybody. I'm Dr. Sherman, and I would like to welcome you here to the planetarium. I don't know if everybody's aware of that. I graduated Valongo Observatory some 20 plus years ago, so I'm very, very, very happy to host this event here with you guys, and I thank the observatory for trusting us with this mission, and I hope you have a great and productive week. Me and my staff here will be at your service for the whole week, and especially the AC crew, because they got a little carried away with the winter part of the winter school. We are trying to fix the temperature here in the room, so you get more comfortable along the day. And I would like to give a special thank to Jorge Marcelino, who is back there working. I don't know if you can hear us. He's back there. Just wait, Jorge. He's like the catalyst. Everything this is happening here is because of him. So big round of applause for him now. It's very good having him on my staff. So without further delay, we can begin with your program. That's you, right? Thank you. Have a very productive week. Oh, that's you then. Okay. Very productive and enjoyable week. Thank you very much.
Okay, thank you. Good morning, everyone. Good morning. Good. So I'm Alan Abertura, from the Institute of Physics from the Universidade Federal de Rio Grande do Sul, and I'm here to introduce our first speaker of this fantastic week. So it's a great pleasure to introduce Manuela Zoccoli, Professor Manuela Zoccoli from the Universidade Católica de Chile. And I met Manuela back in 2004 when I was just a PhD student at the University of São Paulo. So Manuela, she has followed me all the way from that time until now. I also spent a few years in Chile as a postdoc supervised by Manuela. So Manuela has supported my own career for many years. So it's a great pleasure and for education, for science. So it's very good, guys, to see all you young people and keep going. That this long nights will be over soon. So Professor Manuela Zoccoli, she got her undergrad studies and PhD in Italy. She's born in Italy. She's the mother of a beautiful girl. And Manuela, she does lots of teaching, outreach, and research in Chile. And she has, and her collaborators, they have changed totally our view of the Milky Way, especially focused on the galactic bulge. So you have the opportunity to think through the whole week on her lectures. No? So Manuela, she has led lots of beautiful projects focused, trying to understand how the galactic bulge was formed and has evolved. So what else I can say about Manuela? She also spent a few years in Germany as a postdoc, working at ISO. She got lots of great prize in science, and she also has promoted women. I know that. So she has worked a lot in Chile about thinking about the gender gap and the gender issues, trying to attract women to science. And we need that, especially physics and astronomy. So write your questions. And you can also interrupt Manuela during the speak. No? But even in the end, you have like 20 minutes to, to hear all these beautiful questions that you probably have. Manuela, so I will.
I have it here, far away. Guys. Okay, hello everyone. Very happy to be here, especially because I was invited by one of my best postdoc. I'm happy to see that Brazilian community is growing. Should I do? Down again. What should I do? I use the other one. No? No, this is just a pointer. What do I do? I can use that one and forget about it. Okay, so I will be telling you about the Milky Way, our galaxy. And as we will see, I will try to focus especially on the old population, old stellar population in our galaxy. We'll see why I made this choice.
Ela fica na frente do microfone.
As
Ela vira
Alan
pra
told
frente.
you can please interrupt me anytime. Consider that I give classes usually in Chile. I try to calibrate these classes for a graduate student in Chile, but of course every country is different, every city actually, every program is different, so I'd rather be interrupted anytime. Please don't worry about that. Rather than losing you halfway because I said something that maybe is not obvious. This was working a minute ago. Yeah. So I start with a cartoon, very simple cartoon of our galaxy. That I want to make a quick budget of our galaxy. As you know, we live in a spiral galaxy made by a thin disk where most of the mass is, a thick disk, a bit thicker than that, with a bit less mass than that. Everything is immersed in a halo that is very low density. And in the middle there is something, a ball, we will see a lot more about that, that we call the bulge. The mass budget of our galaxy is about this. The stellar mass of the Milky Way is about 10 to the 11 solar masses, and we think there is about 10 times more dark matter in our galaxy. I just put these numbers because then I want to no? Okay. Then I would like to make a quick budget of the different, how much these different components contribute to the total mass. So that is about 5 by 10 to the 10 solar masses. So most of the mass of our galaxy is concentrated here. Some people say 5, some people say 6, 7. Anyway, this is more or less. No? It's approximate budget. And most of the mass of the disk we think is in the thin disk and a bit less in the thick disk. So our galaxy is mostly a disk. Then there is the bulge that has a mass about 2 times 10 to the 10 solar masses. Different measurements say 1.5 or 2, but more or less we are sure it is more than 1 and less than 2. So pay attention to the fact that the mass of the bulge is about one third of the mass of the disk, more or less. So one third of the mass here ignoring the halo in terms of mass because it makes like uh, 100 less mass than the total mass. So it's 1 times 10 to the 9. In the halo, there are globular clusters, but these make up really a completely negligible fraction of the total mass. I'm not saying they're not important, for the halo is not important. I'm just emphasizing the fact that our galaxy is made more or less one third by the bulk and two thirds by the disk. There are other components, but they make up a negligible fraction of the total mass. So in this lecture, we will concentrate on all stellar populations in the Milky Way that are the thick disk, and we will see the thick disk. We think it has more than 7 gigayear age, and it can extend up to 12 gigayears. The bulge is about 10 gigayear old, and the halo is about 12 gigayear old. So we will ignore in this lecture the thin disk, even if it is most of the mass, as I just said, because I decided to concentrate on the old stellar population in the Milky Way. Why? Because they are important to understand the formation of our galaxy. And strange as it may be, galaxy formation is a very complicated problem in modern astrophysics. We really don't know how galaxies form. That might sound like a very strong statement. I'm sure that many of you saw many movies like this that it works. Yes, you have seen, I'm sure, several of those in which you see smaller structures converging into bigger structures and forming in the end things that look very much like giant galaxies, like our own, surrounded by small satellites of every sun. This is the well-known hierarchical scenario of galaxy formation. And if uh, we look at this from this perspective, we might think that we know how galaxies form. The only little problem is that in this simulation, there is only dark matter generally. So there are no stars, no gas, no dust, nothing of the matter we know about. There is only dark matter because it's easier, because we know or we postulate that dark matter particles only interact by gravity. So to run one of these simulations, we have to put mass particles and gravity. That's with all respect for my colleague cosmology, this is a very simplified version of galaxy formation. As soon as we put in there gas, uh, it becomes really a mess because gas starts forming stars, stars hit the gas, then at the end explode. When galaxies interact, um, shock that occurs in the gas may or may not trigger star formation. I mean, the physics of baryons in galaxy formation complicates the picture tremendously. Just to mention a few of the problems. We know that gas must be cold in order to form stars because gravity has to win over kinetic energy of the gas particles. However, as soon as the gas forms stars, the stars hit the gas again. So if we don't get the balance correctly, we are in trouble. We get a model that is not realistic. When does gas form stars? And when does it not? We know we actually using the models a simple description that is called the mechanical law that says that when gas reaches some density, it starts forming stars. We know that this law is pretty good to predict when gas clouds form stars in the Milky Way. But for instance, in the central molecular zone, the central part of our galaxy, there is a lot of molecular gas that is cold, but the star rate is 10 times lower than the mechanical law will predict. So this is just a very simple example to say that we use prescriptions in the model, but we know that those prescriptions fail in some environments. We don't know why. We know that at the end of their leaves, massive stars explode, so they inject a lot of energy and a lot of hot gas back in the medium, and we have to know exactly how much. Because this usually stops star formation. If we don't trial. We don't know what happened to the gas when galaxy merged. And also we are not sure about the role of supermassive electrons. All this was not present in the simulation trial. So it's really a very complicated problem. And the problem is that we look at our universe, how it is today. In order to understand how galaxies form, trial. We need a time machine, to see how the galaxies were in the past. We have two ways of building a time machine. The first way is trial. The high redshift universe. Here we see galaxies as they were when they were babies. And so, trial. Looking at galaxies of different ages, we can have an idea of how galaxies evolve. There are two little problems with this approach. One is the fact that trial. The galaxies move far away. Like these are the babies, but they are points, very small things. And to study stellar population. Trial. To study stellar population of this thing, it is pretty complicated. The second problem is that we in trial. 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 What we call galactic archaeology. We go and look for the oldest stars in our galaxy, and by trying to isolate those, we have an idea of how our galaxy was in the past. Of course, this approach also has several problems, because we know the property of the old stars in our galaxy today. We know where they are today. Maybe in the past they were in a different position, they had spatial position, they had different kinematics, for instance. So anyway, it is a tough problem, and that's why many people study all stars in our galaxy or high redshift galaxies. We are all trying to attack this huge problem for different point of views. So if we want to study stellar populations in our galaxy, whether they are old or young, doesn't matter, what do we want to know about them? Ideally, we would like to measure chemical abundances, because chemical abundances tell us the conditions of the gas when the star formed, because we always measure, by the way, the surface chemical abundance of a star. So normally they are not modified by the fusion thermonuclear reaction that happen inside the star. So this tells us a lot of information of the condition of the galaxies near the star when the star is born. The kinematics tell us how the star move. So, for instance, to which component they belong. The spatial distribution, of course, to know where the stars are, and the ages to know where they were born. So these are the things that we are interested in. And I tell you right away that the first class, maybe my first lecture and maybe half of the second, will concentrate on how do we measure this thing. Because I could show you results, but if I just tell you the end of the story, the results, you might have trouble to read other paper, to understand other approaches. I think it's more didactic to show you the tools we need and how do we measure them, so that you will be able to read critically new papers as well. So in order to know these things, chemical abundances, we usually measure iron and element ratios. In a while I will tell you a bit more about this, why we measure iron and exactly which kind of element ratio are the most important to know the story of the galaxy. Kinematics is radial velocity and tangential velocity. Spatial distribution is, of course, position in the sky and distances. And the measurement of age is very difficult, but we will see that we need distances as well in order to measure ages, because, as we will see, we will need absolute magnitudes. So I want to emphasize that tangential velocity means proper motions and distances.
Trial.
So this we get from spectra. Iron, it's relatively easy to get from spectra, but in order to get element ratio, we usually need high resolution spectra. Radial velocity is pretty easy to measure even from relatively low resolution, low signal to noise spectra. For proper motion, these are really tough because we need time series precise photometry to make astrometry and really see how the star move in the sky. And we need distances to combine with proper motion and get tangential velocity. And the ages will require precise and accurate photometry, especially in the range of old ages, and also or precise and accurate spectroscopy. I put this slide because I want to take the opportunity to emphasize that our view of stellar population in the galaxy has changed quite a lot in the last year, because the Gaia satellite allowed us to measure distances at pretty accurate, at least within some 4 or 5 kiloparsec around the sun for the moment. They will improve even a larger distance. So Gaia had an impact on our measurement of kinematics because it impacted tangential velocity, spatial distribution, of course, and on the age. So it has already been a bit of a revolution in our understanding, especially of the disk, because we can study the galaxy within 5 kiloparsec, but it will be a revolution even larger very soon. Because I will, so now I'm going to discuss how do we derive these things. And in order to be sure we are talking about the same quantities, I need to put a slide about the Cartesian galactic coordinate system. A way to measure positions of the stars in our galaxy is to use this kind of coordinates, in which positions are called x, y, z. X is this axis, so it measures the position of the star in an axis that goes from the sun to the galactic center, usually pointing toward the galactic center. Y is this one, so it is a coordinate that is in the galactic plane, like the first one, pointing in the direction of galactic rotation. Galactic rotation is this. And W, actually, Z, the far away things are the coordinates, and this one are velocity along this coordinate. So Z is the coordinate that measures the height above or below the plane. It's positive above the plane. And so velocities are the corresponding velocity along those coordinates. The velocity around the coordinate x is usually indicated with u, or called the radial velocity. Not the radial velocity along the line of sight, but the radial velocity, there is sometimes ambiguity in the paper. Radial in the sense of sun galactic center. Radial along the radius of the disk in our galaxy. V is the velocity along the galactic rotation, and W is the velocity above and below the plane. This kind of system is important because we will separate sometime galactic component using this diagram called the Thomre diagram, in which, I'm sorry, I have to tell you another thing. Local standard of rest. Sometime we measure velocity with respect to the velocity, to the circular velocity at the radius of the sun. This is what is called local standard of rest. Is a system, just to say very quickly, is a system that is at the position of the sun rotating with the circular velocity that the disk will have at the position of the sun. Then the sun has a very small peculiar velocity along these three coordinates with respect to the local standard of rest. So the local standard of rest moves with velocity in the three components 0 to 120 kilometers per second is the rotation that the local standard of rest has, and 0 is the velocity above and below the plane. So again, the Thomre diagram is a diagram in which here we put velocity v, Sun time it is with respect to the local standard of rest. So it is 0
Trial.
in the sun. The sun will be here, 0, 0, or less. Or sometime it is just V. I will tell you when it changes. But so this is rotation velocity. And in this other axis,
Trial.
we put the tangential velocity, so the square sum of radial velocity and vertical velocity. In other words, every velocity that is not rotation.
Trial.
This diagram is extremely useful to separate galactic components because things that move
Trial.
like the sun concentrate in this region, and things that move differently from the sun move in this direction. So they have lower rotation velocity
Trial.
and higher velocity in the other component. So basically they are less unordered galaxy moving all together along the disk, but more disordered.
Trial.
This, when stars move in this direction, they are more disordered motion in the galaxy. And so it turns out that thin disk stars usually move like the sun. So they concentrate in this region. Thick disk stars rotate slower, but have a higher velocity in the other component because it is a thick disk. In order to be thick, orbits needs to be allowed to go up and down the plane and more radially. So thick disk star concentrate in this region, and halo star concentrate in this other region. So if we want to make a kinematical separation of the different components in our galaxy, we will often use this diagram. Another tool that we will use a lot in order to study stellar population is the color magnitude diagram. I could talk the whole week about the interpretation of the color magnitude diagram, and I don't have a week, so I will be quick. Please stop me if there is something that really catches your attention. Diagrams like that have a color in here and a magnitude in here. Color is blue. Color is, as you know, a difference in magnitude. Usually the bluer filter on this side and the redder filter in this side. So we get blue stars in this side of the diagram and red stars on this side of the diagram. And because this is magnitude, absolute magnitude normally, we have faint stars down there and bright stars down there. This in particular is a color magnitude diagram obtained by Gaia. Why by Gaia? Because in order to put absolute magnitude here, we need distances, and Gaia gave us very good distances. So this is a beautiful color magnitude diagram of the stars within 100 parsec around the sun. So it's mostly thin disk. There is a main sequence in which massive stars are here and low mass stars are there, and the sun is more or less here. Some of the massive stars are already evolved, so these are red giants, these are white dwarf, etc. So we use, in this lecture, we want to make emphasis on the fact that by putting stars in the color magnitude diagram, we can measure ages. The way we measure ages is because the turn-off point, in particular, being the brightest part of the main sequence, when stars turn red, is a measurement of the stellar age. What I'm showing here is the color magnitude diagram of 32 open clusters. Star clusters, in particular open cluster, it's there. It's not me. Okay. Open clusters are simple stellar population, so one age, one distance, one chemical composition. They differ one with respect to the other because the youngest cluster have stars up to here, and as we move to older ages, we move down there. The turn-off of the cluster becomes fainter and redder, and the two oldest clusters we have in this diagram go there. I am assuming that you know some of this, no? So I'm being quick and confused. It's just that this diagram is really beautiful, I think, showing how different population have different turnoff and populate the giant part in different fraction. So there is a simple relation, actually could be analytic even, between the age of the stellar population and the absolute magnitude of the turnoff. But I want to emphasize that in this relation there is also the iron abundance, so the metallicity of the cluster is also present here, actually, and the alpha over iron ratio. We didn't talk about that yet, we will, but this is the particular chemical composition, peculiar chemical composition of each star. However, notice that this coefficient is rather small. So this also has some effect, but it's smaller. This is a bit of a bit bigger effect with respect to that, but the most critical factor is the magnitude of the turnoff getting the age of a stellar population. This is the absolute magnitude of the turnoff, meaning that in order to get the absolute magnitude of the turnoff, you need the observed magnitude of the turnoff, the extinction, and the distance modulus, because these two things together allows you to convert what you observe into an absolute magnitude. Of course, an absolute magnitude is a measure of luminosity of the stars, really. So, this is something that you can get if you have precise photometry, but you also need distances. And you also need extinction. This means that in order to convert what you observe into an absolute magnitude and then in an age, you need to know the interstellar absorption or extinction very well. Usually you know that in regions where the extinction is relatively low, so the halo mostly, but as soon as you go in the plane of the galaxy or towards the bulge, things may get quite complicated. About this art of measuring ages, I also need to tell you another thing. The plot we were looking at was a superposition of several open clusters. Each of them was a simple stellar population, but sometimes you are studying a galactic component or even an external galaxy that is already a complex stellar population, meaning that as a mix of stars of different ages. So you don't see one turnoff, you see something like that. And if you have to measure the magnitude of the turnoff in this diagram, you can't, because there are 100 turnoffs, one on top of the other. So usually the way to interpret this diagram, particularly to assign a star formation history to this population, is to build a synthetic color magnitude diagram. But let me remind you that the star formation history means an age distribution and a metallicity distribution connected. So you want to know, as a function of time, how many stars were born and with which metallicity. So in the end, you know how the stars distribute in age and in metallicity. In order to do that, what we usually do is to construct a synthetic color magnitude diagram, basically a theoretical one, and compare with different input star formation history and compare it to the data. Then choose the best one, the one that best matches the data, and that's our best star formation history. We have seen in lecture 3, because I stole that from my class, we haven't seen in lecture 3, but very quickly I tell you that in order to build a synthetic color magnitude diagram, you need to know the lifetime of the stars in each of the evolved phases. So basically you need to know how long the stars stay in the Aurelian burning phase in order to know how many stars you have to put in this region. And the same thing for every other part. You need to know the lifetime in each of these phases. Instead, in the main sequence, you need to know the stellar initial mass function. These are the two ingredients that you need in order to construct a synthetic color magnitude diagram. Okay, so a few things I want to emphasize on this topic. This is a synthetic color magnitude diagram actually a synthetic HR diagram in the theoretical plane, temperature
Trial.
and luminosity, and this is the equivalent thing converted into observable quantities, so color and magnitude. You see that they are very, very similar,
Trial.
but with some distortion because the color is sensitive to temperature, but
Trial.
in different ways, in different temperature regime. This is not what I want to emphasize here. I want to make you reflect
Trial.
about one thing. This is a color magnitude diagram synthetic constructed for a
Trial.
constant star formation history. So this is an imaginary population, stellar population, that has been forming stars constantly a long time. From zero, I mean stars that have just
Trial.
born, to 13 gigayears ago, uniformly. And we color the stars in different colors. So I want to
Trial.
make you notice that in young ages, an age interval of 0.2
Trial.
gigayears makes such a huge spread in the turn of magnitude. So these are stars that have just born, zero age. It's the zero age main sequence actually. And these are stars that
Trial.
are 0.2 gigayear old. They have a huge difference in the turn of magnitude.
Trial.
Then here, in the blue stars, there is an age spread of 0.5. So these are
Trial.
stars with 0.2 gigayears, and these are stars with 0.7 gigayears. A big difference still for a relatively small age interval, 0.5 gigayear. But down there are 5 gigayear spread in the stars that are red again, so meaning the stars who are here are 5 gigayear old, and stars who are there are 13 gigayear old. They are extremely close. Well, first of all, they have a difference only in the turn-off. Everywhere else, they overlap completely. So the turn-off is the only place in which you have some sensitivity to age in this age regime. Not only that, but the sensitivity to age is extremely small. So this is for you to keep in mind that when we talk about a population that is 10 gigayear old and another author say, no, it's 12, I mean, they are playing with something extremely small. It is really very, very hard to establish if a population has 10 or 12 gigayear of age, or even 8. Instead, it is very easy to know if it is 0.5 or 1 gigayear, because then the difference in the turn of magnitude is huge. Okay. So another thing that I want to mention very quickly, then you read that when you are at home, because, well, at least I am not capable to read and listen at the same time. I just want to mention quickly that when you construct a synthetic color magnitude diagram and want to compare it with an observed one, you have to be creative to decide how do you want to make this comparison, because it needs to be a quantitative comparison. So one way is to pixelize it, to divide it in small boxes and compare via a chi-square the number of stars that you have in each box here with the number of stars that you have in each box here. And then select the synthetic color magnitude diagram, meaning the input star formation history, that best matches the observation, so that there's the smaller chi-square. This is fine in principle because it is very objective. However, in order to do that, while you do that, you forget that you know stellar astrophysics. So you forget that you know that in some region of the color magnitude diagram, you know what happens to the star very well. So your theoretical model can be very accurate. And in another regions, you don't know really how to model those stars. So your model is not very accurate. Given that you know that, why don't you put it in there? So you assign a different weight to different boxes. A low weight to the boxes in which you know that you don't understand stars there very well, and a higher weight in regions in which you know that you can model the stars pretty well. So if you do that, basically you end up modifying the shape of the boxes as well. So you make boxes that compare stars in similar evolutionary phases, in phases in which you understand or don't understand the physics of the star similarly. So basically this is much less objective, but you are putting your PhD in astrophysics in there. So usually people nowadays try to take advantage of many years of study and use the first approach better. Okay, I will stop it here about the ages and move about chemical composition, that is the other tool that is fundamental in order to measure chemical abundances and derive information about where the stars, when and how the stars are born. In order to be all on the same page, we should first realize that people making stellar models measure chemical composition or talk about chemical composition in a different way than observational astronomers. When you take a theoretical model, typically an isochron, most likely you will have a metallicity expressed in Z, because theoreticians used to talk about chemical abundance in this way. They parameterize the abundance of hydrogen, helium, and all the other metals in mass fraction. So they say that the star has a given mass fraction of hydrogen, another mass fraction of helium, and another mass fraction of metals in such a way that these three things should sum to 1, because they are fractions, right? So, just to have an idea, normally this in the universe makes up 3/4 of the total mass, and this is 1/4, and this is marginal. So, first stars in the universe would have precisely what I just said, but with time, a lot of hydrogen is converted into helium in the interior of stars, and so new stars are born with lower and lower mass fraction of hydrogen and higher mass fraction of helium and metals. But keep in mind that metals grow, but still they are, even the most metal-rich stars in the Milky Way have anyway small mass fraction of metals and of helium, and still a lot of hydrogen. This is surface composition, of course. In the middle, close to the core, they could be all helium. The observers instead like to measure chemical composition in a different way with something we call iron over H. Iron over hydrogen in square parentheses. This is the logarithm of the number fraction of iron atoms divided the number fraction of iron atoms in the sun, written there. Okay? If you play with logarithms, you can write this as well like this, or also like this, because the number fraction of iron atoms in a star is number fraction of iron atoms divided number of, number of iron atoms divided number of hydrogen atoms minus the same thing in the sun. It's just a different way of writing the same thing. But just for you, and you can also play with logarithm and say number fraction of iron compared to the sun minus number fraction of hydrogen compared to the sun. Just different ways to write the same thing. But if you have in a star the double of the iron atoms that you have in the sun, the double of the atoms, then you have also the double of the mass in iron, no? So you can go from the observational scale to the theoretical scale with this formula, where, because these are metals, you have to put here all metals, no? If the double of the number of metals, well, if a star is the double of the number of metals, it would also have the double of the mass in metals. And because this is logarithm, you need to do this way. However, this is the same as the iron over H, only if iron traces all the metals. Am I being confused here? Maybe. Right? Because theoreticians measure all the metals, you can go from the theoretical scale to the observational scale if you here put metals. Metals in numbers are the same as metal in fraction, in mass fraction, always. However, the number fraction of metals is the same as or scales the same as the number fraction of iron, only if you can use iron as a representative of all the metals. What I'm trying to say, expressed in a different way, is that originally people made the hypothesis that if a star has the double of the iron with respect to the sun, it also has the double of calcium, the double of magnesium, the double of oxygen, etc. All the metals will be double, will scale as iron. And so we decided to measure iron only because it is easier, I will tell you in a second, and think that it gives us the scale of all the other metals. Because in no case we can measure all the metals, right? No? To measure each and every, forget it. So we choose one, iron, and assume that this scales like all the metals, and so we can use it to go to the theoretical scale. Sometimes this is true, that all the metals scale like iron, and sometimes this is not. However, it is also good, because when it does not, it tells us something about the star, because we think we understand why sometimes it is not the case. It's just that I think that you should have this page, if you were on stellar astrophysics, it might be good to have this page attached in your wall, just to not get lost between different scales. This is another picture that is it's nice, I think, it's beautiful. It has more information than we can discuss right now. It has more information than we need to discuss right now. I just want to, this is just to justify why we measure iron. Because normally the stars are very rich in, this is mass number of the element, and this is abundance of the element in stars. And it's logarithm, of course. So the most abundant element, as you all know, it's hydrogen, followed by helium. And when we go to heavier and heavier elements, they are less and less abundant, except that there are this group of elements that are, in fact, called iron peak elements that don't follow the scale. Even if they are relatively heavy, they are relatively abundant in stars. And this is one reason, one strong reason why we decide to use iron as a representative of all the metals. But the other reason is that we have many iron lines in the optical region of the spectrum. And so it is easier from a practical point of view to measure iron. And so going back to the conversion, and then I stop it because I think a conversion are very boring. Forget about the histograms. I just want to tell you that normally in our galaxy, from the observations we get iron over age, so the number fraction of iron of the stars compared to the sun, and our scale goes from -4 to 1, more or less. Remember that it's logarithm. Halo stars normally has between -4 and -1, -0.9 maybe. These stars go from -1.5 to 0, more or less, and bulge are more metal rich. But this fraction in a phi over h means that this is 0, so the star has the same abundance of iron like the sun. So it will be Z over Z in the sun, 1. Because it's logarithm, and this is 0.1, so these stars have 10 times less iron than our sun, 100 times less iron than our sun, 1,000,000 times less iron than our sun. And if we here put, because we know Z of the sun, that is 2%, the mass fraction of metal in our sun, then the absolute value of this will be 0.002, 0.0003, and so on. Okay, so a quick conversion that you might want to keep in mind. How do we measure this thing in the spectrum? Astronomy 0 slide. How do you form spectra? I go quickly because I think you did this, you saw this, but since it was 5 years ago on average, maybe you forgot. Let us all remember how is that. When we have a source at a given temperature, astronomical, let's say a star, the atmosphere of a star, what this produces is a continuum spectrum regulated by the black body laws that we will see in the next slide. The shape of this is regulated only by the temperature of the star. However, if this, instead of a star, is a thin gas, it will, if it's a thin gas alone, it will emit a spectrum that only has emission line, for instance, a hot nebula. But if we have a black body on top of which there is something gas, we will have a black body continuum with dark, so absorption lines. Quickly, why does the atmosphere of a star emit like a black body? Do you know? Yes. Great. Chileans don't know. But most of the Chileans at this level don't know, I think. Because in the books of physics, normally, the black body is described like this. No, it's a cavity where light can come in, but they will never get out before, this went out, my battery, before doing zillions of reflections. And so in the end, what this cavity, ideal cavity, emits is a spectrum that only depends on the temperature of the cavity and not on the chemical composition, etc., or the incident light. And one might think, what does this cavity has in common with the atmosphere of a star? And the thing that has in common is that the atmosphere of a star is in thermodynamical equilibrium, meaning that, meaning that the light, the photons that are produced by the thermonuclear reaction in the center before getting out of the star to us, are absorbed and re-emitted by the atom zillions of times. So in the end, the property of the light that is coming out has nothing to do with the property of the light that was emitted in the center, but it reflects instead the property of the matter, the atom that it crosses. Okay, so the black body laws that regulate the shape of the continuum are those. The one on that side, the Wien law, says that the hotter the star, the bluer the maximum of the intensity of the spectrum. And here it says that the hotter the stars, the higher the flux at any wavelength, anyway. So this you said you know, so I go fast. I also go fast on the fact that on top of the continuum there are absorption lines. Why? Because when the atom absorbs photons, the electron, one of the electrons, can jump to a higher energy level and then go back to where it was, re-emitting the photon. So why we don't see the photon? Because when it gets re-emitted most likely in another direction. So it's a photon lost, even if it is re-emitted. First reason. The second reason why it is lost is that sometimes the electron absorbs a photon that is very energetic, so it is able to make two jumps. So to jump to 2 level or 3 level or 4 level of energy, and when it goes back, it might go back in small steps. Each of these small steps is a photon, but it's a different photon than the one that was absorbed. So in this second case, the original photon is never seen again. I am more interested in insisting on something that maybe it's less clear to you, and is the fact that sometimes when the stars are cold enough, you have molecules in the atmosphere. Molecules could also absorb radiation because they have different energy levels of vibration and rotation. The molecule is made by 2 or more atoms, and these atoms have a different energy according to the frequency of oscillation like that or rotation like that. These energy levels are also quantized, whatever. And so molecules can jump to different levels of energy, so vibrating or rotating at different frequencies, but to do that, they need to absorb photons. However, the difference in energy between different levels of vibration or rotation is much smaller than the difference in energies between atomic level. For this reason, while atoms produce lines in the spectrum when they absorb photons of a given energy, molecules produce bands like that. Like that. Because bands are many lines very close to them. Each of these lines corresponds to a different transition between level. And because these levels are very close one to each other, the lines are packed and in the end produce a band. So what I want to get is to the fact that cold stars that have molecules in their atmosphere are full of molecular bands in their spectrum. And this makes their analysis very, very complicated because you don't know how to define the continuum. Thank you. Because you don't know where to find the continuum to take as a reference to measure the depth of a line. Let's keep this in mind because it will be useful in a short time. So from the spectrum, here I really go quickly because it is astronomy 01. From the spectrum you can measure the temperature of a star because as we learn in the first year, the appearance of a spectrum, both the continuum and the strength and the quality of the lines you have change with temperature. So these are hotter stars and these are colder stars with molecular band in it. The temperature increases in this way. And this is the famous slide with the solar spectrum in which you see that in a star similar to the sun, you have really zillions of lines of different elements. This is H-alpha, for instance. This is H-beta, the triplet of magnesium, the doublet of sodium, and so on and so forth. So we measure the strength of these lines, of one line, for instance, corresponding to a given element, in order to know how much of this element there is on the surface of a star. What do we measure? We measure the equivalent width. So we measure how dark the line is, basically. How dark the line is would be, if this is the spectrum, would be the integral below this curve. The integral of the curve between the continuum and the line. This integral. In practice, for some reason that is not completely clear to me, astronomers decide to parameterize the area in here, this integral, in terms of an equivalent width, which is the width that the line would have if it was squared. So if it was between the continuum, take as a reference like 1 and 0. So if I take this area and redistribute it in a squared line, I could measure the area with only one parameter, that is a length, no? Because the 8 of this square would be 1, goes from 0 to 1. So the 8 of the rectangle, that would be basis times height, If the height is only 1, will be just the basis of the rectangle. So with the linear measure that we call equivalent width, we give a measure of an area, which is the area below the line. Now we need to convert this area into an abundance. And I want to spend just one easy slide to remember that in order to do that, the resolution of the spectrum is extremely important for two reasons. Here I plot a spectrum with high resolution, so in which you can really separate small regions of the spectrum very well. In a high resolution spectrum, you see the line very deep and very narrow. When you go to lower resolution, you see the line with a larger width and a lower depth. So two things happen, because you're smoothing the line basically if you have lower resolution. Two things happen. One is that if you have a small line, you lose it, because smoothing them, you lose the line. So in low resolution spectra, you cannot measure small lines. And the other thing that happens is that in an isolated line, you can measure it pretty well, whether it is with high resolution or with lower resolution, doesn't matter. But if you have a crowded region of the spectrum, when you lower the resolution, first of all, you merge several lines, so you don't resolve them anymore, you blend them. And second, it becomes very hard to decide where is the continuum of this continuum line. So you don't know where to set the zero level from which you need to measure the line. So this is to say that, of course, low resolution spectra are easier to obtain because you can get higher signal to noise quickly, but it becomes harder and harder to measure chemical composition in lower resolution spectra. And I have a very complicated slide with many equations, but we need to think one moment about this fact. In order to convert equivalent width into abundance, it is necessary to calculate how many atoms of a given element can contribute to a given line. What does it mean? It means that in a few stars, for instance, in a star, in K-giant stars, in a star as cold as 4500 Kelvin, for instance, the Balmer lines, hydrogen lines, are very weak. Instead, in a A-type stars, a star with 10,000 Kelvin of temperature, Balmer lines are very strong. What does it mean? That A stars have a lot more hydrogen than K stars? No, right? Stars are anywhere, always dominated by hydrogen. But in some stars, you almost don't see hydrogen in the spectrum. And this is because when the stars are Balmer line in particular are line that corresponds to the jump of the electron of the hydrogen between level 2 and level 3. But if the star is too cold, you don't have any electron in level 2. You have all of them in level 1. So you cannot have the jump between 2 and 3 if there is nobody in 2. And if the star is too hot, you have all the stars in level 5. So again, with the hydrogen electron in level 5, so you will not produce the jump between 2 and 3 anyway. So in order to convert the strength of a Balmer line that you see into abundance of hydrogen, you need to know which fraction of the hydrogen has the electron in level 2. So is potentially able to produce the line. Okay? If only 10% of the hydrogen has the electron in level 2, you have to multiply what you measure by 0.9, by 90, a factor of 90 in order to get the whole hydrogen. I mean, in order to take into account all the hydrogen that you are not seeing, because it's not able to measure, to produce the jump in the spectrum. This is kind of elementary, but I see lost faces. I don't know if it's because it's obvious, you're sleeping, or you got lost. Please, raise your hand if you want me to repeat this. Yes? Yes. Absolutely. Can I write somewhere? Yes. We have the hydrogen. The hydrogen atoms is the most simple atom you can have in the atmosphere. Has some energy levels in which its only electron could be, right? Okay. So here we have. Thank you. Here we have the spectrum with wavelength here, and I don't know, H alpha here. The H alpha line corresponds to the jump of the electron from level 2 to level 3. Okay? So in order, you produce this line when the hydrogen in the atmosphere makes this jump. In order to produce this line, you need that the hydrogen atom in the atmosphere has the electron in here, in the first place. For that, you need a given temperature of the star, of the atmosphere of the star. Because if the atmosphere of the star is colder, then you have the electron in here. Because if it's colder, the hydrogen atoms have less energy, and so their electrons are at a lower level. Okay? If you have a star with all the hydrogen atoms with their electron at level 1 in the fundamental state, these atoms are not able to produce H alpha line because they cannot jump from 2 to 3 if they are not in 2 to start with. If the star is too cold, the hydrogen in its atmosphere will be most likely up here. So we'll have the electron at a higher level, a higher energy level. So if the electrons are up there, they cannot jump from here to here because they're not here, they are all there. So in this case, which is the case of a very hot stars, you will not see any H alpha line because you have no hydrogen atoms with electrons in here. So if you have in order to convert the strength of the H alpha line that you see into an abundance of hydrogen, you need to estimate how many hydrogen atoms have the electron in there so that they are potentially able to make this jump. Of course, at a given temperature, you will never have that all the hydrogen has the electron here and all the hydrogen has the electron there. There will be a distribution, and that's the next slide. No, the next slide, no, this slide. So you need to know, as I said, how many hydrogen atoms have the electron in level 2. And how do you know? Because this specific question is given by this specific equation, Boltzmann equation, that tells you the number of atoms that have the electron in level, that are in level E of excitement, so have the electron at level E, divided by the number of atoms that have the electron in level J. This is given by a given expression of quantum physics that we cannot discuss at this moment, but the only parameter that may change in the atmosphere of a star is the temperature. All the other things are, these are the energy of the respective level, and these are constants that you can find in any books. So the parameter that really affects in the star this population is the temperature of the star. You have this other equation, much more complicated, that tells you also which fraction of the atoms is ionized compared to what fraction of the atoms are neutral. So you might even have in the atmosphere of the star some hydrogen that has completely lost the electron, and of course this will not be able to contribute to the H-alpha line. So this tells you which fraction of all the hydrogen you have is neutral, so has the electron, and which fraction has the electron in level 2. You also need to put these other two equations because this is the Planck law that tells you the continuum, so how many photons come from the interior that may or may not be absorbed, and this is how many jumps you can have, not because a photon was absorbed, but because the atom collided with another atom. So you need to put all these equations in your code in order to convert the measured equivalent to it into the abundance of the atom. And I want to emphasize that the things that are relevant, the parameters that are relevant in all these equations are the temperature of the star in here, and in here, and in here, and in here, and the electron pressure in here. The electron pressure, that has something to do with the density of the star, of the material in the stellar atmosphere, and so with the gravity of the stars, that is directly related with the density. This affects the fraction of the atoms that are ionized. So basically, in order to make this conversion from what you measure from the spectrum to an abundance, you need to know the temperature and the gravity, or the density, is the same thing, of the star. And how do you know? You need to build. Am I past my time? Yes, right? I spoke for 1 hour and 10. 5 minutes. I only tell you about the model atmosphere and then we have questions. In order to analyze a spectrum, because it's easier, sometimes you say, yeah, there is the line, you know the abundance. Instead, there is all an art and very complicated between what you measure from the spectrum and the astrophysical quantity you derive. In order to know the temperature and the gravity, to model these two things, not to know. In order to model this, you need a model atmosphere. Why do you need the model atmosphere? Because the star is not a ball. It doesn't have a hard surface. It's a sphere of gas. So when we say the surface parameter, we say something very, very, very imprecise because there is no surface in the star, right? So we see the sun. We say that the surface temperature of the sun is 5,770 Kelvin. That's the temperature of the photosphere. But when we take a spectrum, we are seeing the photosphere very well. And we are seeing also a layer that is slightly below this photosphere. We see it too in the spectrum. This is a layer that is hotter, and we don't see it completely. We see half of the light from it because it is a bit deep. And we also see a layer that is below that is even hotter, and we barely don't see it until there is a level that we really don't see it. So the model atmosphere models the fraction of the atmosphere of the star that we do see. This model tells us the photosphere is 5,770 degrees and you see it completely. So you see everything that it emits. If you want to say it more formally, the optical depth is 1. It's 0. This is the scale of the optical depth. You have it fresh. You see it completely. How does it go? The optical depth 1 is that you don't see anything, right? And 0 is where you don't see. Yeah, okay. Anyway, you see everything from the photosphere of the sun. When you go 1, the model atmosphere tells us this is a layer with this temperature and this gravity, so this electron pressure, and you see everything. Then there is another level that is slightly hotter, slightly more dense, so you have to put other numbers in the equations before, and you see half of it. And then there is another level that is even hotter, even denser, and you see it barely, and then there is nothing that you see. Okay, you have this model. In order to know how much you see of this level, if you see it completely, if you see half of it, if you see it barely, if you don't see it, you need to need to fit in the opacity of each layer, actually of this layer and the layer above that. And the opacity is what is to model the bound-bound absorption, the bound-free absorption, the free-free absorption, the electron scattering. So everything that could absorb photons between this layer and the end of the star and makes you don't see what is below. So there is all of this physics inside the model atmosphere, and for each layer described by a model atmosphere, you have to solve these equations in order to be able to go from the equivalent width you measure to the abundance of the element. So if it is an art, and actually a kind of a black art, it's not surprising that you need to fit in really a lot of physics. And we usually do the model atmosphere with all these assumptions, that it's a plane parallel geometry. Now there are some models that are spherical, but they are not the most. That the atmosphere in hydrostatic equilibrium, that there is no fine structure, so spots in the star, etc., and no magnetic fields. Once you do all this, you can do the conversion. In practice, the model atmosphere, I just told you that needs to know the temperature and the tells you that a star like the sun, so for a given temperature, will have the layers as I told you. So in order to construct the model, you need to know the temperature of the star and the mean log G and the metallicity, because the metallicity affects the opacity. Can go back. But you remember that we had the opacity at some point to tell us how deep in the star we see. And the opacity depends on the metallicity. That is kind of the smog that you have in the star. Elements that can trap the radiation. But this is what you wanted to measure. So how do you know it? In order to build the model atmosphere to fit in the code, it's an iterative process. Basically, it's written there, then you read it when you are at home. Otherwise, you get confused now. Basically, you guess the temperature, the gravity, and the metallicity of your star before measuring it. You guess it. Then you measure the metallicity from several lines, and if you guessed it wrong, you get a different metallicity from each different line of the same element. So you know you got it wrong, go back and change it until you get it the same abundance for every line you measure. So this is to say that you need to measure many lines. And in particular, I want to go back just a second to this equation, then I stop. You need to measure many lines corresponding to different jumps in order to constrain the temperature, but you need to measure different lines corresponding to different ionization states in order to constrain the gravity. Because if you have the gravity wrong in your model, you measure the same abundance for every line of the same element, but a different abundance from lines corresponding to different ionization state of the same element. If you don't have those, you don't realize that you have the gravity wrong. Okay? This is another reason why we choose to measure iron in the spectrum, because in the optical region we have many lines, of course corresponding to different jumps, but we also have lines of iron at different ionization levels, iron neutral and iron ionized ones, and by means of these two we can constrain gravity. I think I need to stop, and I will be very happy to take questions.
Okay, guys. Okay, first question here.
Hi. Can you go back to the slide that you show the metallicities and the parts of the galaxy, like the budge, the halo?
Yeah, these were very, very, very approximately, huh?
Yeah. So in the halo, we have the older stars of the galaxy. So is it wrong to think that older stellar population had produced more elements and more iron, so they would be they would have more metal parts?
I understand your question. There are two parts on your question. First of all, it is the opposite, because we are measuring the surface abundance. So it is true that older stars, you might think that older stars have cooked more element, had more time to cook more element, but in the center. So we measure the surface, so all the stars, like all stars were born a long time ago. And the interstellar medium from which they were born was very clean, very devoid of metal. So it was the other way. The older stars are more metal. However, this relation that we apply all the time is very approximate. We should keep in mind that with time, the metallicity of a region of the universe increases because more stars produce more and more elements. So we can think that the older stars are more metal poor and the younger stars are more metal rich in their surface. Only if we consider a very isolated region of space. If you compare a star 13 giga-year-old in our galaxy and in the Large Magellanic Cloud, even if they are both 13 giga-year-old, they will have different elements. Actually, 13, maybe they will be similar because they are the first stars that formed. But if you compare a star of 5 giga-year in our galaxy and in the Large Magellanic Cloud, their surface composition can be completely different because all the evolution that happened in our galaxy is very different from the evolution that happened in the Small Magellanic Cloud. So it's a very, very approximate relation between metallicity and age.
But in the nucleus of the stars, there's no convection that brings iron to the surface.
It's never this big. There is some mixing that brings to the surface some elements, but usually they are the lighter element, like C and O elements, and this is one thing. But it's very marginal. So there are some elements whose composition is not the composition you measure is not the primordial one, but it's been affected. But only a few elements. It's true only for a few elements and for the stars in some evolutionary phases.
Okay, thanks.
Remember also that older stars, you have to fit in also the lifetime of the star in this, no? When we see a very old stars, we only see small stars because the massive stars that were born 13-year-old are way dead. And so the rate at which stars produce the element is not the same for a massive star and a low mass stars.
Okay, this is very, I think that's very basic, but if you go to that plot, you have the abundance of the different elements. I think it's...
At the beginning, yeah.
Yeah, this one. So you said that, I think that in general for the students it's very confusing this, because we go there and you see the oxygen and carbon peak, and then you see the iron.
Yeah.
So for me it would be logic that we go and measure the oxygen and carbon instead of the iron. Why not?
Yes.
In the surface of the stars.
In fact, we do, but in the optical region, we have oxygen and carbon in molecules. So they are oxygen, carbon, and nitrogen usually are present in molecular bands. And so they're very hard to measure. But in the near infrared, tomorrow I will talk a bit about that, you have atomic lines of these elements as well. And so they're much easier to measure. Actually, oxygen you measure atomic only in the optical, but for the other two, you need to go into the infrared in order to measure their abundance.
Yeah, I think that there probably the point is that making the distinction of measuring these elements in the stars, because if you go to the gas, it's completely different.
Yeah.
And then I'm all the time, what's this point? I mean, it would be perfect if you could measure the same, the abundance using the same process.
There is another important point that is kind of hidden here. It's not only that you have a different abundance in the star and in the interstellar medium, but it's also based on the technique you use to measure, to get the spectrum, and on the region of the spectrum you analyzed, you have different elements available and different kind of transition. In some case atomic transition, in some other case molecular transition. So what you measure in stars and what you measure in the interstellar medium is driven in many cases by the technique and the spectrum interval that you can measure. So it is true that her point was that usually people measure in the star a given set of elements and in the interstellar medium another set of elements. And so it becomes harder to make the connection between the stars and the interstellar medium. This is a limitation, I think, of observational strategy.
And you have lots of ion lines in the optical one, so it's much easier.
Yes, so it's easier, yeah.
So in your second or third slide, you showed us the mass budget of each galactic component. Do you have any more information about how the mass of the thick disk was estimated, if it comes directly from the orbits of the stars, or is there a different method?
It's very approximated. It's super hard to measure the mass of this component, all of them, in particular those that are very much spread. So yeah, usually people make models, dynamical models, in which they measure the orbits and derive the potential. This is all the information I know. I took that, can't remember the reference, tomorrow I will bring it. I took that from one of the last papers on the thick disk using the orbits made with Gaia. So it's more or less the best we can have, but it's anyway very, very uncertain. I will give it a factor of 2 uncertainty. Yeah.
Hi, thank you. I have a question about the Cartesian plane slide. I didn't get what's up with the angles.
Let me find it. You didn't get?
The angles here in Z, X, and Y.
Okay, so these two axes are in the plane of the galaxy. One from the sun to the galactic center, and this other at 90 degrees with respect to the first, so in the direction of galactic rotation. Okay? And this is vertical. So, of course, there are 90 degrees between each of these axes. So I am the sun, there's the galactic center, one axis is there, the other is there, rotation, we all rotate like that, and the other is above and below.
Go. No one? Want to ask anything?
Can you show us again the HR diagram from Gaia? this cloud of stars below the main sequence, it seems to have an empty space, or more or less populated space here. Yes. Is there any reason, or is just error?
I think it's observational, some observational bias. I guess those are blends or more or cataclysmic variables, but they should be a small fraction of those should be cataclysmic variables, but more of them are blends. Halo stars, more metal poor should be like that, no? Still very close to the main sequence. So stars here, I'm not sure what they are. I think they are some observational artifact.
Okay, any other question? No? So I think let's thank Manuel again. And you'll be back here later, no? 2:30 after the lunch. But I think before you leave, Manuel, would you like to take the photo now? Or to take the picture?
Yeah, I want the picture with you, please.
Like a self.
I can go there and take the picture with you guys. Yeah, to go there. Go there. I could do it. Up there it would be very easy.
Obrigado.